Hello, my name is Taylor Marion, and this is my final project presentation for CSE 722 with Dr. Austin O'Brien. I chose to do a malware classification project using Windows portable executable imports. The goal of this project is to develop a machine learning model for classifying software as either malware or goodware based on static analysis features. The dataset includes 47,580 entries derived from the PE import element of Cuckoo Sandbox reports, with features indicating the top 1,000 most imported PE functions. The original source of this dataset is the IEEE data port. Now, the features of this dataset include a hash value, an MD5 hash value, which acts as an identifier, 1,000 binary features, each representing a imported PE function, and the target class label of malware, 0 being goodware, 1 being malware. Here are some high-level overviews, a nice little header file. Now, I'm going to try to go really quickly because all of my rehearsals went way over 10 minutes. So I'm going to try to go quickly but not miss anything important. And for acknowledgements, the malware samples were originally received from virusshare.com, and goodware samples were taken from portableapps.com explicitly for Windows 7 directories. So this serves as a model, but for implementation in modern use, you'd want to look for Windows 10 or even Windows 11 files. Here's a high-level notebook structure just to organize my thoughts. We'll address each of these individually. We're going to import libraries, nothing really exciting there. And one of the reasons why I really like this data set is that a lot of malware detection relies on signatures and soft features like IP addresses or domain names, which can be easily changed. So this only analyzes more concrete things of what the software is actually doing. So hopefully it will be more resilient against like domain changes and soft name changes like that. We're going to load the data set, do a quick sanity check just to make sure that the information looks the way that we're expecting it to look. Cool, no surprises there. We're going to head over to data pre-processing. The first thing we're going to do here is drop the hash column because that's a identifier but is not used in any of the fitting or the training of the models. We're going to look for missing data. This data set does not have any missing data. So it's a little bit boring, but as a thought experiment, if it was missing any data, I would be inclined to just delete those records. We have 47,500 something records, so missing a few records here and there would not be statistically significant. And more importantly, because all of the features are binary, I can't find any meaning in using a average or a k nearest neighbors approach to imputing that data. I don't think that would be anything of meaning or of substance, so it would just be an arbitrary value, and I think that would throw things off. But we don't have any of that missing data, so we can move on. Moving on into exploratory data analysis. The first things we did here was just take a look at the class distribution. Now, we can see that this is a very imbalanced data set with about just under 96% of the data being malware. Now, this is to be expected because malware can be changed and modified, replicated, copied, redistributed, and shared around. So it's expected that we're going to have a lot more malware than goodware. We do need to be aware of this when it comes time to split those data sets, though. First thing I looked at was the most positive and most negative correlated features. Now, we can see here, none of these features are extremely strong. They'll have a strong correlation. Now, this tells me that we're not looking for those one or two magic import functions. We're really looking for some unique combination or some more complex interaction between features. A lot of this stuff I'm just going to kind of glaze over simply because during my initial analysis, I was just looking at, well, this might be useful, this might be useful. I don't know what I'm doing, but this might be useful down the road. So long story short here, we can see a lot of things are co-correlated. We have a lot of colarity. We have a lot of pairs up here, but it's not enough to really get rid of any single functions here or there. So we're going to move on into dimensionality reduction. Now we have 1,000 features for each of our 47,000 records. That's a lot of processing time. So the first method I approached to reducing this dimensionality is principal component analysis. Now the goal here is to reduce features down as much as possible into components while still retaining 95% of the explained variance. We can visualize this here, so we can see that we pretty quickly, we get down to 72 principal components. And when you look at the first few components, we can see that the first one explains for 35% of the variance, the second one explains 21% of the variance, and it pretty quickly goes down. This can be visualized here on this graph. It goes up pretty quickly, and then pretty quickly, right around 20 or so, we kind of hit this point of diminishing returns. So I went ahead and I ran this a few times over with different percentages of explained variance, and at 95%, we have 72 components. As we creep up to 96, 97, 98, 99, we just get more and more and more and more because each of those additional components just gets smaller and smaller and smaller. So I thought that 95% served as a really good reduction, it's a great reduction while still explaining for the vast majority of the variance here. For each of our methods, I did a little trick here to save time, where I saved the data set to a file and then I read it back from the file. Just so if I close the file, I could come back and read it quickly and work with those data sets without having to do the reduction over again. Quick sanity check for the principal components, and this again reinforces that no single feature is really strong. We're looking at these unique combinations. Second method was using the recursive feature elimination. This method basically takes all 1,000 features and then strips off one at a time until we get down to a target of 72 features. I chose 72 because when I was first doing this, I'll be honest, I was a little underslept, and I said, well, PCA got us 72, so we'll do 72 here. I ate a snack, I took a nap, I came back, and I realized, components is not the same thing as features, but it worked pretty well. And when I Googled a rule of thumb, I kept finding either 50 or 100 were a good starting point. And since 72 is in the middle, it served pretty good. So a little happy accident, and I stuck with it. Going through recursive feature elimination, we get down to these 72 features, which are here. Same thing, I saved them as a CSV so I could easily access them again without waiting 106 minutes to redo it every time. Third method here is lasso regression. This method is a little less interpretable in terms of what the result is going to be. With PCA, we can say, hey, I want 95% explained variance. With RFE, we can say, hey, here's a target number of features to reduce down to. With lasso, you can fine tune that using hyperparameters, but it's not as explicit as saying, I want 72 features. But lasso came down with a list of 779 features that were, impactful. Now, that's definitely less than 1,000, but that's still a lot of features to go through, especially compared to the 72 we have with RFE. We go ahead and save that data to a CSV file for easy access. Do a quick sanity check, make sure that none of our transformed data sets have any missing values. It's exactly what we expect it to be. Now, I was curious how much of our recursive feature elimination data set and our lasso data set overlapped. So 66 of the 72 RFE features overlap with lasso. So that tells me that, they're both looking at least some of the same stuff. Before we get into training, we need to split these data sets up. Now, as I mentioned above, this data is very imbalanced between goodware and malware. So we use stratification to make sure and to reinforce that all of our data sets are being split evenly along class distribution. I used a default value. This is actually from your code, but I think it served really well here. A training size of 80%, a validation size of 15%, and a testing size of 5%. Now, because we have such a large data set, I wanted to put as much effort as possible into training and validation. And for testing, even 5% still gives us a really good size for testing the models at the end. So using 80% training and 50% validation really allowed us to focus on fine-tuning the models as much as possible. But like I said, with 5%, we still have quite a bit. We still have 2,379 samples for testing, which is a good size. We go ahead and split these up. We do a sanity check here, making sure that we enforce those class distributions of roughly 96 and 4%. Looks good there. We move on to model training. The two models we chose here are logistic regression and random forest. Now these are both binary classification models, so they serve us really well. For logistic regression, we use that early on in class. So it's a pretty simple algorithm, a pretty simple model. It's efficient for highly dimensional data sets like this one is. And because it's simple, it serves as a really good benchmark for more complex models. Now, we also chose random forest because we did not cover that in class, and I wanted to cover at least one model that we didn't talk about in class, just as a bit of a challenge and just to kind of broaden my horizons. So random forest is an ensemble model based on decision trees, and it's really good at handling nonlinear relationships and feature interactions. Random forest in particular can also account for imbalanced classes, which we definitely have here. Now, going into the evaluation, we use cross-validation, which we'll talk in more detail in a moment for. Going into the cross-validation and the training of these models, there's a few metrics we need to keep in mind. Accuracy is how many predictions were correct out of all predictions. Precision, how much of what we said was malware is actually malware. Recall, how many malware cases did we detect? And the F1 score being the balance between precision and recall. So for the context of malware detection, I prioritized recall because in a lot of environments, you really want to catch as much malware as possible. And if you get a few false positives, well, that's okay because you can inspect them and then improve them later. But once malware is on your network, that's bad news bears, so you really want to avoid that at all costs. So I prioritized recall in all of my training and testing. We use cross-validation here to test the metrics for each of these models. Now, essentially that cross-validation is going to split that data set into 5 folds. It's going to use 4 of those folds for training and the 5th set for evaluation. It's going to repeat that all 5 times, 1 for each fold, and then give us the final results at the end. So we use cross-validation to evaluate, and then we fit the model using the full data set. I do that for the full data set of 1,000 features, and then each for the PCA, RFE, and LASSO transform data sets. We come down here, we see the final results. They all performed really well. Pretty similar scores for accuracy, precision, recall, and F1 across the board. The biggest difference here is just in the computation times. We can see that the RFE data set did all of that in less than a second, where some of these, I think the full data set, just for comparison, took almost 12 seconds. So considerably longer. Moving on to the random forest model, we did the same thing here. We used cross-validation for the data sets. We split we use that against the data sets we have, the full 1,000 features, the PCA, RFE, and LASSO data sets. Pretty similar results overall, all very close. Now we can see that this model did take considerably longer. Even the shortest, the quickest was, again, with the RFE data set with 6 seconds, whereas the PCA data set took 47 seconds. So considerably faster computation times. And running this one time for evaluation isn't too bad, an extra 30, 40 seconds, who cares? But when we get into hyperparameter tuning, we're going to be running a lot of permutations on this. So because the scores were so similar overall and the computation time was significantly shorter, I chose to use the RFE data set moving into hyperparameter tuning. We used hyperparameter tuning, specifically using a grid search to test out every possible combination of all of these hyperparameters here. Now, for some of these models, some of these hyperparameters are non-compatible with each other. So we do get a lot of errors, as you can see down here, but it essentially just gets an error and then just moves on to the next set, and it just says, it alerts you, but it just moves on. At the end of the computation time, we have our best parameters and our best recall score. And our best recall score is a 99.98%, so really high recall score, excellent. We move on to, we do the same thing for random forest, looking at all these different computation models or different combinations of hyperparameters. We find a similar really high recall score, and we have our best parameters. So now we're going to move on into model evaluation, which is using those best parameters, and we're going to look at those more closely. Specifically, we're going to look at things like the confusion matrix, we'll look at the scores, the RSC curve, and we're going to compare some of those metrics. This is a function I built out to test out that specific model using those best parameters. So I describe the best models here with those parameters that we found above. Go ahead and I evaluate those as accordingly. So this gives us a little our test results here. We can see that our accuracy is at 96%. So that's a really good score. It tells me that it's well fit without being overfitted, especially because this is being tested against the validation set. This is not the same model, or not the same data set that was used for training. So 96% is a great score, and recall is great. That's 99.99%. So we can see here logistic regression. We only had one piece of malware slip through the cracks. We did, however, misclassify a lot of goodware. The RC curve here, essentially this dashed line represents just random guessing. So we're doing considerably better than random guessing, which is good. We have our random forest evaluation, which is pretty similar overall, better at detecting goodware, but still have some mixed results there. Really similar overall. Now, one thing that we have not adjusted yet here is the threshold value. Binary classification models like these use a default threshold of 0.5 or 50% to determine if something is malware or goodware, 0 or 1. So because our models are trained and tuned to prioritize recall, and we get a lot of these, false positives here, I thought, well, maybe if we adjust our threshold value to prioritize F1, we can keep that high recall, but maybe, find a better balance and get more precision out of it to get less false positives. So I used the precision recall curve here to kind of analyze where that highest threshold value or where that best F1 score is. And I used those threshold values of 0.84 for logistic regression, and random forest also got roughly 0.84. So I used those values to evaluate those same models, but with that increased threshold. Now we can see overall we still have a really good score, but when you look at the details here, we went from having one piece of malware up to 35 pieces of malware slip through the cracks. We're better at detecting goodware, but going from 1 to 35, that's a big jump in malware. Looking at the random forest with that higher threshold, we see similar results. Now, we finally are accurately predicting goodware more than miscalculating it, which is good, but at the risk of having more malware slip through the cracks. So depending on the environment, that is just not an acceptable ratio. So we're going to keep our default values at 0.05 for threshold. Moving on into testing, now that we have tuned and we have our threshold adjusted, we're moving on into testing. So using the test set here, so using our trained and tuned models against the test set, logistic regression gives us a perfect recall. No malware slips through the cracks. Looking at random forest, pretty similar. Two things sneak by, so it's still good, but just not quite as good as the logistic regression. So to summarize the findings here, the best performing model is the logistic regression model using trained for high recall and using the default threshold. Now, my recommendation is to use that set moving forward because its scores are so high and it offers extremely reduced computation time. That would be my recommendation moving forward. So some potential improvements going forward for this would be, instead of prioritizing recall from the very start, maybe we could, in the training and hyperparameter tuning stages, prioritize F1 from the start and then adjust the threshold to maximize recall. So at those different stages of training, tuning, and then threshold adjustment, play around with different priorities of precision, recall, and F1 scores. That's a similar approach to using the grid search, where you're just going through those different computations, those different combinations. So do that at like at a meta scale, so to say. That might allow us to keep that high recall, but not misclassify so many pieces of goodware. So that would be my recommendations moving forward for improvements. At the end here, this is just a little time saver for myself, so I could save these models and then load them back up, so I didn't have to do all that work all over again every time I wanted to play around with something. That being said, I know I've gone way over time. I apologize, but thank you for this semester, and I hope you have a great break. Thank you.